Unfortunately, Matt couldn't be here, which is great for me because I get to give a talk to all of you. Not so good for you because you get me and not Professor Matt Rowan. But regardless, I think it's a really good opportunity for me to speak to like this wide range of audience from people that are just learning this type of thing to like the experts in the field of intractable likelihoods, of which I am definitely on this end of the scale. This is sort of my first foray into this area. I was just a student, a PhD student in my second year, wandering around the forest, that is research, and I just happened upon an intractable likelihood that, to be honest, at the time I probably didn't even realise was an intractable likelihood. I just sort of, this is the way that I got around this problem, so I'm going to introduce that to you today in the hope that it's a relatively simple solution and maybe you have some ideas of a more complex way to do this more efficiently. So I work on networks in general. More specifically, I'm interested in social networks and how these social networks impact how we interact with each other. So because we're connected, we will talk over these connections, and how can we sort of find this connection between our network structure and how we talk to each other. So I'll give a brief introduction of networks. We had a really nice one yesterday from Ricardo, so I won't delve too far into that. And then, like I said, a little simple application of an MCMC method to sample some of these things that we might not be able to do otherwise. And then also introduce my current work, which is extending this to dynamics on top of networks in this area of network inference. So we can skip over this slide. Basically, it's just a pretty picture. Nodes, edges, lots of modelling applications that we saw yesterday, and we have many different ways that we can construct our networks. So lots of different models, lots of different ways you can go and collect your networks of all different types. So one way that many people play with networks is to go and get one. Whether you scrape it off the internet or you collect it through surveys or something, this is one way that you can do network research. And this is fine in some sense, but often we sort of want to be able to answer questions about typical graphs and not just about the single graph that we found that one time. And so as we saw yesterday, Ricardo was introducing random graphs or random networks, and I'm just going to use graph and network interchangeably here. It depends how I'm feeling at the time. So we have this idea that there are many types of random networks that we use to model what we observe in the real world. So we observe some property of a network in the real world, and we go away and try and find a model that will model this property for us. So we use random networks to get a distribution of these things, so we can answer questions about typical graphs. And most of these models are actually based on construction. So you have a way to generate these networks. One of the most famous is the Barabasi-Albert preferential attachment model, where you start with a few nodes, and then nodes enter this system and connect with other nodes, preferentially to those that have a higher degree. So you get this rich get richer phenomenon and end up with a power law degree distribution that we see in a lot of real-world networks. But of course, this is just sort of a construction, a way to construct these algorithms, not so much the sampling and the likelihoods that we may have seen yesterday. So there's a bit of a disjoint between the way that we can sample these networks and how we could maybe write down something like a likelihood for them. So in some cases, we don't know much about them at all, except the fact that we can create them. And in other cases, like the Erdos-Renyi, or there's some spatial random graphs that we're going to see in a minute, where you can write down something about this likelihood, but perhaps if you want extra properties, you can't write down a closed form. So we're going to focus today on the second case, where we know something about the likelihood of our underlying model, whether that's an Erdos-Renyi or a spatial network. But we also want to condition it on an extra property. Say that we know that our graph is connected. Right? We don't want to just sample from the space of all graphs. We want to condition it on something. So we focus here on connected graphs.
By connected, do you mean fully connected, or so no synchrons?
By connected, I mean that there are no isolated components. There's a path between every pair of nodes. Not a complete graph. So the distinction is that we don't have every single edge there, we just have a path between all edges, so we don't have two disconnected components. And so I did come across this while trying to simulate connected networks, obviously, and I just try my accept reject algorithms, and you sit there and you sit there and you sit there and you sit there, and you kind of figure that you need something a little bit better than waiting. So to introduce this, we're going to look at a spatial random graph, so I'll introduce that next, and then how we can sample connected versions of these graphs. So we're going to assume a Waxman network. Waxman network because Matt loves these networks, but spatial networks in general because often links are expensive. So if you're creating a network, especially physical networks, links are expensive to create. So if we're going to go and build the NBN network, we're going to have to dig the holes to lay the fibre, and it's a lot cheaper to dig smaller holes than it is to have longer links. And this is also observed in social networks as well. It's a lot easier to maintain a friendship if you can see people, if you can see them, if you can communicate with them, than it is if the people are farther apart. So, of course, this has decreased a little bit with online social networking and this sort of thing, but in general, you do still see this phenomenon in social networks as well. So for the Waxman network, we have each node with a position in some space, and we're going to just connect these nodes with some probability that's inversely proportional to our distance. So in this case, we just use the exponential, decreasing exponential. So this is quite a simple way to incorporate spatial structure into our network and still be able to have a way to write down the likelihood of each of these networks. Which is just the product over the edges that we have in our network and the edges that we don't. Sure is. Did I? Yeah. I must have changed that to be consistent later on. Missed that one. Yes, nodes I and j with probability Pij. So here's an example. I just put it. It's pretty easy to simulate these. Just have some each pair draw a random number and connect with if we accept that edge. So you can see that we have more shorter edges here, and so you can see that this is dependence on distance. Not to preempt anything, you can also see this is disconnected. Which leads to the fact that we don't have connectedness in many cases, and this is a crucial property in many networks, especially in real-world networks. There's not really much point building an electricity tower and not connecting it to anything, or an electricity plant and not connecting it to anything. So it is often the case that we do have connectedness in our networks. And where I came across this is in social networking, when you're looking at the people that have seen a particular tweet or have seen a particular piece of information, they've all seen it from somewhere. So they're all connected in some way. And so if we want to try and propose networks like this, then we need to be able to have a connected network. And in general, in Waxman networks, Erdos-Renyi networks, connectivity is a different thing to ensure. So the question then becomes, can we sample these graphs? And like I said, we can use a basic accept reject algorithm, but for many parameter values, this is just too slow. Maybe if you just want to run graph, you could sit and wait a little bit, but if you want to propose many graphs, like in an ABC context, this is just going to be prohibitively slow. So the next step after that is to have a go at Metropolis-Hastings MCMC techniques. So that's where we went with this one, with just your basic Metropolis-Hastings algorithm. So the first thing you have to decide is your proposal step. And so we're trying to move from one graph to another graph. Okay? So I need to have some way that I can move through this space of graphs and be able to try and explore the whole space. So there are many algorithms that use switching. So you have two you pick 4 nodes and you just switch the edges that are between them. Okay, but this maintains the number of edges, and of course in this Waxman graph we don't have a fixed number of edges, so you need to make sure you have some way that we can get more or less edges. So the most basic thing possible, which is where I always start, is to just add or remove edges one step at a time. So choose 2 nodes, I and j, and if there's a link there, you get rid of it for your next step. And if there's no link there, then you add it in. Okay? So really simple, 2 graphs, 1 edge is different. Okay? And this is nice and reversible or symmetric, it cancels out nicely in the acceptance probability. So we then end up with our acceptance probability. I've already cancelled out the proposal steps, but this still is not easy to calculate because we said before we couldn't do the calculation of this probability conditioned on our connectedness. But if we just impose the condition that every graph in our chain is connected and never accept graphs that are disconnected, this actually all drops out really nicely. So if our graph becomes unconnected, we reject straight away because the probability of that graph is 0. And if our graph is connected, then we can have these conditionals drop out nicely because we assume that probability of connectedness is constant over the ensemble of graphs. Okay? And so we have a much more simple acceptance ratio here. Now there could be some issues with calculating this ratio in some types of problems where perhaps you don't have independence of edges in your network. But with the Waxman network, drops out really nicely. It's just the ratio of having that edge in the graph to not having that edge in our network. And so this is really quick, and you can calculate these edge probabilities almost instantly. Alright, so I usually put this in, you guys probably so familiar with Metropolis-Hastings that this may be just beating at something you already got, but we have this Waxman network we had before, and I've just put in a really long link to demonstrate that this is quite an unlikely Waxman network that we probably wouldn't want to sample many times. And our algorithm is just going to, we propose we add this edge, we'll add the edge, and then propose we remove, and then remove this edge. And now we have a more likely Waxman graph. And of course, many, many edges pop in and out over this algorithm. Now convergence here I struggle with a lot because, I mean, when is it converged? It's a graph, and then the graph ensemble is so large that you can never really picture it nicely. So we do have to use summary statistics of our network, and then if you believe that if your summary statistics converge, then your graph is converged, then we're all good. If you don't, then it becomes a little bit trickier. So we do show, didn't put the graphs in here, that the summary statistics you can do a nice trace and do all your convergence statistics on these. And then you can also do a really small example, so say a 5-node network or a 6-node network, where you can enumerate every possible graph in that case. And so you can look at the distribution here over time and see that it does converge to what you would get in an accept-reject algorithm that is okay for these small graphs, so we can get both results there. So the third thing that I wanted to talk about is what I'm doing at the moment. So with this convergence complexity, just quickly, in that it's pretty slow. I mean, Metropolis-Hastings is not known for its speed, and of course as you get to bigger graphs, this is going to be almost prohibitively slow. So we have to add edges individually. So of course we have to get to every edge eventually some number of times for convergence. So we're looking at an order n squared convergence as you increase the size of this network. And I mean, it's not the worst one you've ever seen, but it's also not the greatest. So we're looking for ways that we can try and improve this, whether it's through the proposal distribution, or whether it's through a different method to try and speed this up. So the third thing that I'm doing at the moment is extending some of the work of dynamics on networks. So this is information flow, epidemics, all these types of things, and putting them on networks to try and work out this relationship. So information propagation is just the movement of ideas across a network or in a population. So people talk. They like to copy each other and do things that other people are doing. So if my friend's wearing some pair of shoes, maybe I'll go out and buy the same shoes in a different colour or something like this. So we all look at each other, and information, ideas, products can spread across networks. So this occurs in the offline world, obviously, and it's become a lot more prominent in the online world, on Facebook and Twitter, where people can copy other people's ideas and share them, and they can kind of spiral out of control in some cases. So it's a really topical idea at the moment of this information flow and how it comes about. And of course networks are critical for this. So this was first studied by Granovetter in crowds. So if one person writes in a crowd, and then the other one person sees someone else and thinks, okay, I'll write as well. And so you have this sort of cascading effect in a crowd. But obviously in the real world, I don't see what everyone else is doing. I only see what my friends are doing or what my connections are doing. So it is really natural to model these cascades over networks. And so what I'm really interested in is this connection of what does the network structure tell us about how people talk and how ideas can spread. Do they spread faster with certain network properties or slower? And so in this way you can try and promote your product on Instagram if that's what you want to do. Or you can, if people are talking about protests and rioting, you can try and work out how you can place your resources to then try and stop this from becoming violent. So the problem that I'm looking at the moment is kind of the inverse of this. So if we observe people talking, which of course is a lot easier with things like Twitter, can we then infer the underlying structure? So can we infer that because I retweeted Ace on Twitter, that we're friends, or that we have a link? So there's been a little bit of work done on this in the MLE context. You observe some set of cascades, where in this case we just say cascades are the times at which someone posted something, or the times at which they did something. So you just have a string of the node that was activated and at what time. So they do some work on MLE estimates of this sort of thing, where they simplify and simplify and simplify their likelihoods until they can get something that's tractable. What we're trying to do is put this into a Bayesian framework to try and get a little bit more information. Because networks are such complex things, just because one network was the most likely doesn't mean that there's not another network that shows you a different path that this information could have spread through the network. So it'd be really nice to have distribution of networks that can tell us more information about this sort of thing. So we do have to assume a few things, as always, but for now we assume that our underlying graph is Erdos-Renyi. Very basic assumption, and you can obviously extend it pretty easily to Waxman and a little bit more difficult to extend to other types of random graphs, but we just assume Erdos-Renyi for now. And we also have to assume a cascade model. We have to assume the way in which stuff moves over our network. And one of the most basic is the independent cascade model. Okay, so the independent cascade model works on a network in the following way. Someone knows something and they want to share it. So they share it and their friends accept this with some probability beta. Okay, and then they obviously don't with 1 minus beta. So we have this probability that you accept this contagion in the propagation, in information propagation, or the chance that you were infected if you're being coughed on. something like this. So we then have this over all the edges that we have and that we don't have, and we also have a probability term in there between the nodes. So the basic assumption that a lot of people make is that if I share something, and the people that share it first are more likely to be directly connected to me. Okay, so if we share things closer in time, we're more likely to be connected. So this is the assumption that most people make and that we make here, but you can make this as complicated as you want. Maybe you're both of some class, or you both have a certain degree. That may make propagation more or less likely, so you can incorporate that. And then where it gets not so nice is that you have to sum over all the possible ways that information can flow in your network. So here in this small example, if node 1 starts the flow, and node 2 is infected next, and then node 3 is infected, there are a couple ways this can happen. Either node 1 infected both node 2 and node 3, or node 1 infected node 2, and then node 2 infected node 3. Okay, so we need to sum up over all the possible trees in our graph. And so we get this cascade likelihood, where we have a sum over all the trees in our graph that this cascade propagated over, and then the likelihood of that tree having a cascade. And of course it's the sum that makes this intractable. To sum over all trees in graphs might be fine in really low graphs, but it's not long before it becomes really quite hard to do. So I have never put up a theorem in a talk, but I'm going to give it a go. I'm not going to explain it too much, but if we notice here, we have to try and calculate the probability of each tree. Okay? And so Kirchhoff's theorem, extended to the directed case by Tutt, does this really nicely for us. You can count the number of trees, either undirected or directed, in your network. So we use this, we create the Laplacian matrix, which is to do with the number of edges that each node has. And if you take the determinant of this matrix, it will count up the number of trees, or it will take the product of the weights, which in our case are probabilities, and give you the weight of this spanning tree. So this simplifies it a little bit, in that we can put this instead of this awful sum that we have, and then I've just sort of also put it in a ratio which we're going to need for our MCMC algorithm. So this is kind of where I'm up to with this project, in that this is a nice little model, and so we try and put it through an MCMC Metropolis-Hastings algorithm. And of course we use, like I said before, we use the Erdős-Rényi prior, but you cut out a lot of graphs. Your space becomes a lot smaller because some graphs just can't facilitate the cascade you observe. If you observe node 1 and node 2, they're the only two you observe that activate, then there must be some link between them. So you get rid of a lot of graphs that way. So it works all right for small graphs. This is a 10-node network. On the right you have the actual graph. Yellow are the edges that exist and purple don't exist. And on the left you have the distribution over the edges. So in the distribution that you recover, you determine the edge probabilities from here. So you get some sense of the distribution over the edges in this case. And you can see it's doing pretty well. There's not much structure in an Erdős-Rényi graph, so you can't really say that we're picking up structure or anything, but at the moment I'm implementing on graphs with more structure, so you'll be able to sort of see it a little bit better, hopefully soon. But it's not awful, and it does all right on your ROT curve, depending on whether you believe that a ROT curve is a good way to determine how well this is doing. But in a lot of the computer science papers where this comes from, ROT curves and precision recall curves are how they determine how well they're doing. So it's not doing too badly in that respect. This is a 10-node network, obviously. As you make it bigger, it does break pretty quickly, but you can do 1,000 nodes, and depending on how many cascades you observe, you can get a reasonable estimate in terms of the area under the ROC curve. But again, we run into this very slow algorithm idea that we have graphs which are really big, and we're only doing this link by link with the same proposal that we introduced before. So in any case, however well you want to do, you have to go over every edge at least a couple times. So this just isn't feasible as soon as you get to, I would say, big graphs. Matt would say small graphs, but like millions of nodes. Okay, so this is where sort of the extension of this comes in, and sort of coming to this workshop to be able to listen about all these possible methods to use in this problem. So, you know, can we change the proposal that we can explore this space faster, but still be able to get from one between all graphs that are possible? We don't want to make this disjoint, because it's quite easy to never be able to get from one graph to another, say if you restrict the edges. Alternative methods or an alternative setup, something like SMC or importance sampling seem like a really good idea, but requires a lot more effort on my part, and also understanding of these things to then translate to graphs, because it's all easy when I can draw my little normal distribution of my parameter, but in this case it's a lot higher dimension than that, and we can't do something like that. And of course something else is that maybe this independent cascade likelihood isn't worth it. You could maybe get a different likelihood that could then scale a little bit better, or is possible to have sort of each node updating separately so you can parallelize over the nodes themselves. And then I guess the main question is, once we have this knowledge of the distribution of graphs, the few people that have attempted this don't really utilize this information. So they say, you know, we've got a really probable graph here and a really probable graph here. It's like, that's all good, but how can we use this to make decisions or sort of intervene in certain situations, or, you know, can we predict the links that we think this graph could use to create sort of information flowing more easily? And I'm going to leave it there, so thank you all for listening. I'm sorry I'm not Matt, but maybe next time.